All right, welcome everyone. Today, we're going to break down some really core concepts in chemistry. We'll start with the basics of how we measure a solution's strength and work our way all the way up to the amazing systems that keep life in balance.
So it really all kicks off with a super simple question. I mean, if you've got a glass of water, salt water, how do you actually put a number on how salty it is? That's exactly what we're going to tackle first.
Okay, so here's the game plan. First, we'll figure out how to measure the strength of a solution. Then, we'll look at the super simple art of making it weaker, or dilution. From there, we dive into a truly weird property of water that, believe it or not, unlocks the secret of the pH scale. And finally, we'll see how these clever chemical systems called buffers manage to keep everything in perfect balance. First up, measuring solution strength, or what chemists call concentration. This is really all about putting a number on how much stuff, that's the solute, is dissolved in a liquid, which we call the solvent.
So one of the easiest ways to do this is with what's called mass/mass percent. You just take the mass of whatever you're dissolving, say salt, divide it by the total mass of the entire solution, so the salt plus the water, and then multiply by 100. Yeah, it's really that simple.
And it's pretty much the same deal if you're mixing two liquids together, like alcohol and water. You can use volume/volume percent. The logic is exactly the same. You're just using volume instead of mass. Then you've got this kind of hybrid mass/volume percent. You actually see this one a ton in medical settings, like for saline IV drips. It's just comparing the mass of the solute in grams to the volume of the solution in milliliters. Okay, but let's be real, the absolute king of all concentration units, that's molarity. Now, instead of grams or milliliters, it uses something called moles. You can kind of think of a mole as a chemist's dozen. It's just a specific, huge number for counting atoms or molecules. So molarity tells us how many of those dozens of molecules are packed into 1 liter of solution. And this is the unit chemists use all the time, because chemical reactions, they happen molecule to molecule, not gram to gram. All right, let's actually put this to work and see how it goes. To figure out the molarity of this salt solution, it's just a few simple steps. We basically just take the numbers we have, the mass of the salt, its special molar mass, and the volume in liters, and pop them into the formula. A little bit of math, and we get our answer, a 2-molar solution. Okay, so you've made your solution, but what if it's too strong? What if you need to make it weaker? Well, that brings us right to our next topic, the simple but totally essential process of dilution. And this right here, this lays out the core idea perfectly. When you dilute something, the amount of the stuff you dissolved, the salt or the sugar, that amount stays exactly the same. All you're doing is adding more solvent, like water, which spreads those same molecules out over a bigger volume. And believe it or not, this whole process boils down to one super elegant, super simple equation. C1V1 equals C2V2. The concentration you start with times the volume you start with equals the new concentration times the new volume. This little formula is a chemist's best friend for cooking up solutions with just the right strength. All right, let's switch gears a bit. We've been talking about the stuff in the water, but now let's talk about the water itself, because it turns out water has this really strange and incredibly important property that is the foundation for all acid-base chemistry. And that leads to a pretty wild question. Can pure water, all by itself, act as both an acid and a base at the exact same time? I mean, that sounds kind of impossible, doesn't it? Well, believe it or not, the answer is yes. It's a process called autoionization. What's happening is that in any glass of pure water, a teeny tiny fraction of water molecules are always reacting with each other. One water molecule donates a proton, acting like an acid, and another one accepts it, acting like a base. This creates these two ions, hydronium and hydroxide. Okay, but here's where it gets really cool. At 25 degrees Celsius, if you multiply the concentrations of those two ions together, you always get this exact same tiny number. It's a fundamental constant of nature called Kw. It's like they're on a chemical seesaw. If the concentration of one goes up, the other has to go down to keep that product locked in at that exact number. This perfect balance is the key to everything that comes next. So let's take that weird fact about water and see how it leads us directly to something you've definitely heard of, the pH scale. It's our universal standard for measuring acidity. So here it is, the famous pH scale.
Basically, if you have more hydronium ions than hydroxide ions, the solution is acidic, and its pH is less than 7. If you have more hydroxide, it's basic, and the pH is greater than 7. And if they're perfectly balanced, like in pure water, the pH is exactly 7, perfectly neutral. But where do these nice, simple numbers even come from? Well, it's actually just a clever math trick. This formula might look a little intimidating with the log, but look, all it really does is take those super small, awkward numbers for ion concentrations and turns them into this nice, friendly scale we all know from 0 to 14.
And just so you know, there's a mirror image to this called pOH, which does the same thing for the hydroxide ion. And because of that special constant for water we just talked about, the two are always connected. It's super simple. pH plus pOH always equals 14. So we know pH can go up and down when you add acids or bases. But what if a system, say a living thing, absolutely cannot let its pH change? And that brings us to our final topic, these amazing chemical systems called buffers. So what is a buffer? You can think of it like a chemical shock absorber for pH. It fights back against big swings in pH because it's got a two-part defense team, a weak acid and its partner, which we call a conjugate base. And that's really just the molecule that's left over after the weak acid has done its job and given away a proton. Okay, let's watch this defense system in action. So imagine a strong acid gets added to the solution. The H+ ions are the invaders. Immediately, the conjugate base part of the buffer team swoops in and reacts with them. The buffer basically gobbles up that strong acid and turns it into a harmless weak acid. And the result? The pH barely even moves. So what happens if the invader is a strong base instead? Well, now the other half of the buffer team, the weak acid, jumps into action. It donates its proton to neutralize the strong base, preventing a big pH spike. It's this beautiful two-part system that keeps everything stable. And look, this isn't just some abstract thing in a textbook. This is literally the chemistry of life. Your own blood is an incredibly fine-tuned buffer, holding its pH steady right around 7.4. Which brings us to a final, really important thought to leave you with. What do you think would happen to the trillions of chemical reactions that are keeping you alive right this second if that buffer wasn't there?